this should be 34th, right? No, 30.
35.
35th, yeah. So hello and welcome to the 35th lecture in this series. So let me resume from the last lecture. We had discussed the Picard existence and uniqueness theorem, which implied the existence of integral curves of any vector field on any manifold. But I wanted to point out that we have something stronger than just saying that integral curves exist. So what we have is the following statement. Let X be a vector field on a smooth manifold and P belong to M. Then there exists epsilon greater than 0 such that epsilon greater than 0 and a neighborhood of and an open set V containing P such that first for any Q in V there is an integral curve sigma Q defined from minus epsilon to M with sigma Q0 equals Q. Again, the point is that the same epsilon will work for all Q inside this neighborhood. The interval of definition of the integral curve is not shrinking. The second thing is that the smooth dependence on initial data. So the map let's again continue to call it G from this V cross minus epsilon to M defined by G of Q comma T is sigma QT. So here I should say that there is a unique integral curve with this property. So in fact that's how I am able to say this moment you know Q, the sigma is predetermined, of course, given X. So the map defined by like this is smooth. This is a smooth dependence on initial data. And this completely this is the best one can say without assuming anything further about the manifold. For instance, it turns out that if the manifold is compact, then every integral curve can be defined on the domain can be taken to be all of R, not just some small interval minus epsilon. But in general, without any further assumptions on M, this is the best one can do. Now, since I've talked a bit about this interval of definition, let me quickly give an example to illustrate why we need to even mention this. So on R, let X be the vector field. So remember that on Euclidean space, a vector field is just defined by a function from the open set back to the same Euclidean space. So on R, a vector field would be given by a smooth map from R to R. Vector field defined by phi of t is t squared. So i.e. X at any point t, if one thinks in terms of derivations, this is t squared times d by dt, derivative at that point. Or in terms of functions, this is just phi of t is t squared. So now let's look at integral curves of this vector field. So the defining property, if sigma is an integral curve of integral curve of x, then sigma prime t would have to be equal to x at sigma t. In other words, this is thinking of it as in this Euclidean terms. So this is just sigma t squared. So in more familiar notation, if we think of a function y as a function of x or t, this we are looking at the equation y prime equals y squared with some prescribed initial data. So let's solve this. Y prime equals y squared, y of 0 equals some, let's say, alpha and r. We know that the solution always exists by Picard's theorem. Actually here in this case we can explicitly solve anyway. So if we solve this, we'll solve it in the usual way. Y prime by y squared equal to 1, assuming y is not 0. Then I integrate between 0 and, so integrate this between, so put a dt, oops. So what I get is using substitution and so on, what I end up getting is y of t. So here this is the derivative of actually minus 1 over y prime dt 0 to t. Actually I can just use the fundamental theorem of calculus. So this is minus 1 over yt plus 1 over y0, y0 is alpha, so it's t, and then I play around with the, so I take it to the other side and so on. 1 minus alpha minus t equals 1 over yt, or yt equals 1 divided by 1 by alpha minus t equals, no, let me just leave it like this. Now at t equals 0, of course here when I did this, these calculations were formal calculations without paying any regard to whether y is 0 or not. But once I have this formula, what I have here I can disregard these calculations and then just check directly that this is indeed a solution to this y prime equals y squared, and y of 0 is actually just is exactly equal to alpha. So this is a perfectly legitimate solution, and we know that this is the unique solution beginning at t equals at the point alpha. Now the point is that let's see what is the interval of definition of this. So this makes perfect sense until t equals 1 over alpha. So as long as t is less than 1 over alpha and there's no other constraint on t less than 1 over alpha, one is in good shape. Oh, if alpha is negative, then it's even then. So we just want to ensure that we want to have 0 in our domain of definition. So this is here if alpha is positive. If alpha is negative, then I would want t greater than 1 over alpha and no other constraint. Yeah, these two cases arise because I want to impose the condition that 0 is inside the domain of the solution. So now the point is that as alpha changes, so the domain is either, so for the moment let's fix alpha greater than 0. In this case the domain is minus infinity to 1 over alpha. So as alpha changes, the domain of definition does change. So for instance, as alpha goes to 0, then this becomes larger and larger. On the other hand, if alpha is actually equal to, if alpha goes towards infinity, then the domain 0 should always be in the domain. So but it gets closer and closer to 0, just goes slightly past 0 on the right side. So the point is that even though we started with a very simple case of R and a perfectly smooth, in fact it's a polynomial vector field, still the domain of definition of the solution is not so, it's not that it's always going to be all of R. And also another thing one can notice here is that let's note that the vector field is actually equal to 0 when t is 0. So if I had taken alpha to be actually 0, then this will not work anymore. So all along I had assumed that, so these calculations break down if alpha turns out to be 0. This has to be treated slightly differently, and in fact here's a small corollary of the uniqueness part. If X is a vector field on a manifold M and xp is the 0 vector, then the sigma p t equals p for all t. So the integral curve which starts at the point p is the constant integral curve. It just stays there for all time. So even in this case of y prime equals y squared, the solution when alpha is equal to 0 is just y of t is 0. The 0 solution is the only one for all t. And this is true by the uniqueness part. So let's just check this. Define gamma from R to M by gamma t is the constant curve. Just take the constant curve. Then gamma prime t, it's a constant curve, and whatever definition of derivative, however one likes to calculate, it's easy to see that you get 0. So the 0 vector, and this should be equal to, so this is 0. On the other hand, the 0 is also x at, by assumption, this is xp, which is also equal to x at gamma t, since gamma t is the constant curve. So what we end up concluding is that the integral curve equation holds for gamma. Therefore, gamma t, and we know that integral curves are unique, so gamma t equal to sigma pt, and so when I make the statement about uniqueness and so on, one should, to be careful, one should always mention the domains. So here, for instance, when I say sigma pt, the normal thing to do is let you specify sigma p to be the integral curve defined on the maximal domain on definition around starting at p. So in other words, start with some integral curve at p, see how far you can extend it, take the largest possible interval and work with that. Otherwise, you can always restrict to a subinterval and still it would be a solution and there would be ambiguity. But that's more of a technical thing. So with that understanding, this gamma t is equal to sigma pt, and one is done. So this is equal to p, rather the left hand side equal to p. So when a vector field has a 0 at a point, the integral curve is just that point itself. Now we also talked about the smooth dependence on initial data. That actually gives rise to a very interesting construction in the setting of a manifold. So let's call this corollary 1, and corollary 2 is for simplicity, let me take the case. So actually one need not restrict to this case, but let me take the case when the integral, suppose all integral curves on M are defined on R. So one must be careful that this is a somewhat, this is a non-trivial condition. As we saw, even the simple quadratic polynomial vector field on R does not, this condition is not satisfied. The intervals of definition are of this form, minus infinity to 1 over alpha or 1 over alpha to infinity. So in particular, they are not all of R. But there are lots of other examples where this condition does hold. All integral curves on M are defined on R. Then the map G from M cross R to M defined by Gxt is, so just look at the integral curve starting at x at time t. So this map is smooth. So this is now this follows from what I said earlier, the Picard's the last part of Picard, this statement here, smooth dependence. Now this in the Picard's theorem, I had to restrict to this V, a smaller open set V, on which I could make this statement that this is smooth and so on. But one can check that, in fact, and smaller open set and right. So one can check that actually even in this case, so I won't go into too much of detail here, that on the, for one thing, smoothness is always a local issue. So for example, here I can restrict x. If I want to check smoothness at a point x naught t naught, I just have to restrict to an open neighborhood of x naught and a neighborhood of t naught, and then consider this. So I don't have to work with all of M and R. So in fact, this does follow from the Picard statement. So one gets this map, and not only that, if I fix, now let's turn it around, and in fact what we'll do is, let's fix this t and regard it as a function for, if we fix t naught, we get a map M to M, which is x going to sigma x at t naught. Let's call it G subscript t. GTX, no, GT naught x is sigma x at t naught, which is just g of x t naught. So I regard it as a function of one variable. So all we are doing is, we are taking any point x, what the map does is take any point x, look at the integral curve starting at x, travel along that for time t naught. So you'll end up with sigma x t naught. That is your new point. So to every point on M, I've associated another point of M. That's this map from M to M, like this. And the claim is, for any t naught, GT naught is a diffeomorphism of M. So this family of maps GT is called the flow associated to the vector field. So the moment you have a vector field, you have integral curves. Using integral curves, you get this flow, and the flow consists of diffeomorphisms of M. Now, how does one see that this is a diffeomorphism? The smoothness of, well, you have to check that GT naught is smooth and bijective and its inverse is smooth. The smoothness of GT naught just follows from the smoothness of G, since all I've done is I fixed one variable regarded as a function of the other variable. So this is smooth. Now to see that G is bijective, there's a neat way of seeing this. Namely, just notice that if I now note that for any S and T in R, GS composed with gt is g of s plus t. If we have this, then it's immediately clear that, and also the other thing is, when I take t not equal to 0 and g0 is, well, if I put t naught 0, I'll be looking at sigma x at 0. So the integral curve which starts at x, I want to see where it is at time 0. By definition, it is at x. So this is just the identity map. So gs composed with gt is gs plus t, and g naught is identity. This implies that gs composed with g minus s is g naught equal to identity. And so therefore g has an inverse, which is gs has an inverse, which is g minus s. G minus s is gs inverse. So this proves two things. One is that gs is bijective. The other thing is the inverse of gs is also of the form g of something, therefore it's also smooth. So it immediately follows that it's a diffeomorphism. Now this statement, the gs composed with gt, is just, I won't do this, but I'll just write the basic reason, follows from uniqueness of integral curves. So in short, if all integral curves are defined for all time, then one has a nice family of diffeomorphisms of the manifold which depend on a single parameter t. Not only that, this family of diffeomorphisms gt, t belongs to R, is actually a group in the sense that, and a composition. If you compose two of them, you get one more thing like that. And identity is inside that because G0 is identity, and inverse is there because of what we just saw. So if you have a vector field with integral curves defined for all time, then, and as I said, there is one very important case where integral curves are defined for all time. So this is a theorem in ODEs actually, which I won't prove. If so, first let's say that, let's give it a name when integral curves are defined for all time. X is complete if all integral curves are defined on R. Then the theorem is that if M is compact, any x and M, any vector field is complete. So in the case of a compact manifold, one has this nice flow and so on. But even if it's not compact, if the vector field is complete, one has such a flow. So all right, so we'll stop here, and then I'll see you in the next lecture. Thank you.